Good evening to all of you. And today
Good evening.
we'll good evening. Today we'll discuss the techniques in remote sensing and digital image processing, that is DIP. So, lot of process, lot of satellite data are used for different applications and different projects, and different characteristics are also there for different satellite data. We will discuss all these different characteristics and different features of the satellite image and their functions. So now we'll start with the raw and path. So generally क्या होता है कि suppose one satellite is capture some data, so they are capturing in this way. So there is a path and row is there. So there is a unique ID for each satellite image. So all these satellite images are created by the satellite sensor with some tiles are there. The square tiles or rectangular tiles are there. So each tile have some row and path information which is unique to each satellite image. So this is the row. So this is the path. This vertical direction is there. So this is the path of the satellite. Then these are the rows. So path are like 191, 190, 189, 188, 187. So these are the path of the satellite which captures the images in this way. And these are the rows informations 51, 52, 53, 54, 55. So likewise, all these information, suppose we have to download one satellite image from different site or any others open source site, then we get the satellite data like this. This is the Landsat 8 satellite image. So this is the one tile. So it is 191 by 51. So 191 is the path and 51 is a row. So this way, all the satellite data are created and we have to download tile by tile. And suppose we have to work for more area, then we have to add some satellite image or mosaic this satellite image, all these tiles, and join into a one mosaic satellite image or merge image. After that, we have to work in a single satellite image. But before that, we have to acquire, archive this data in this tile format, and each tile have different bands. So for Landsat data, a lot of bands are there, more than 8 bands are there. So each uh, tile have 8 to 12 bands. So we have to download all these band in zip file. Then as per our requirement, we have to compile all these bands. Suppose blue, green, red, infrared, there is a need of 4 bands. Then we have to join all these bands and create a multispectral image from this tile. So in this tile or in this satellite image, so the width and the length is 185 kilometer into 180 kilometer. The swath is this like this 185 into 180. So this type of area is there, and for different satellite image, for list 4, list 3, and Sentinel, their area is different and their dimensions are different based on their resolution and other factor. The tiles area are different. So this is the basic things about the satellite image acquiring, how to acquire the satellite image, how this is look like during downloading this data. So in this satellite data, we have also seen some cloud are also seen. Cloud data are, ये जो white patches दिख रहा है ये सब cloud area है. So we have to avoid this cloud data image. So in USGS side, we have to check whether it is cloud free data or cloud bearing data. So we have to query that I have to download the satellite image which have less than 5% of cloud. So they search all these satellite image, then they give the cloud free data, because if the cloud is there, then the analysis for uh, different work is very difficult and a lot of errors are found. So you have to avoid some cloud data satellite image. But in microwave satellite image, there is no cloud. All the satellite image are cloud free data due to the high wavelength characteristics. So these are some example like uh, Landsat 7, Landsat 142 by 151. There is the path and row information. All the satellite data all the satellite data have some metadata information like what is the date where of the acquisition of the satellite image, date and then path, row, and resolution of the satellite. All these informations are included during our download. So a lot of informations are also there. So these are called as metadata. So data about data or information about the data is called metadata. So this is like this, and we just forward this. Then aerial photography. Generally, aerial photography used for high resolution images, as satellite image is not capable of having high resolution, spatial resolution of images due to the height factor. बिकॉज जब हम सेटेलाइट इमेज देखते हैं 800 टू 600 टू 800 एल्टीट्यूड में रहते हैं, तो इसीलिए उसका रिजोल्यूशन एज कम्पेयर टू द एरियल फोटोग्राफी थोड़ा सा कम है। लेकिन एरियल फोटोग्राफी में हम ज़्यादातर 10 सेंटीमीटर स्पेशल रिजोल्यूशन का इमेज हम पा सकते हैं। जैसे 10 सेंटीमीटर रिजोल्यूशन मीन्स ईच पिक्सल इज 10 सेंटीमीटर इंटू 10 सेंटीमीटर। So there are a lot of informations we can gather with the help of aerial photography, and or for urban planning, flood mapping, aerial photographs are highly usable. So the process of capturing photograph of Earth's surface from airborne platform. So it is not a space-borne platform. Airborne platform means 10 to 12 or 20 किलोमीटर above the Earth surface. अगर हम 10 से 12 किलोमीटर के हाइट से अगर कुछ एयरबोर्न प्लेटफॉर्म फ्लाइट से कुछ सेंसर यूज करके कुछ फोटोग्राफ लेते हैं with the help of different sensors, then it is called as the aerial photograph. The science of making accurate measurement from photographs, especially for mapping purpose. So you get the accurate photography, and for different use also we use aerial photography. But it's had some unique phenomenon like this. Each flight, suppose this is the area which capture in at a time. एक साथ अगर at a time इतना area capture कर रहा है, the next image is 60% overlap with the first image. So this is the characteristic of aerial photography. So इस इमेज में जो है फर्स्ट इमेज, देन सेकेंड इमेज एंड थर्ड इमेज, so each image having the 60% overlap. That so why this is 60% overlap? So for stereoscopic model, 3D and data analysis or creation of 3D image, so we have to create some overlapping area so that the creation of 3D is very much easy for us. Then this is the flying height, that is the height equal to focal length by scale. So suppose what is the flying height we have to know. Then focal length, if it is given 0.5 inch, and then we have to divide it in by 1 is to 2000 scale, then it is calculated it. This is the 1000. That means the height is 1000 meter. That's why we can calculate the height or focal length or scale of the image. Suppose we have given the focal length and height of the altitude of the uh, from flight, then we can get the scale of the photograph, aerial photograph. Then some camera are mounted and overlapping images. This is the satellite image. Then this is the aerial photography from flight or any helicopter, and then some UAV are there. So, effective surveyed. Why we use this aerial photography for surveying, disaster assessment, urban planning, and agriculture. So these are the major factor where we use surveying, disaster assessment, urban planning, and agriculture. Then some terms are used in the aerial photography like scale. Scale is generally the ratio of image distance to ground distance. So what is the scale? The distance between the two objects in the aerial photograph with respect to the distance between the two objects in the ground. So this is the scale. So the scale is generally the ratio of the distance in the image to distance in the ground. So for that we can calculate all the scales. Suppose 1 into 10,000 scale means one unit, whether cm or 1 meter, 1 cm in image, then 10,000 cm is in ground. So likewise the scale is calculated. Then relief displacement is also one of the factor in aerial photography. The average shift in position of object due to terrain elevation. Suppose एक elevation area की वजह से अगर कोई शिफ्ट हो गया, then there is called as relief displacement. उसको हम नेक्स्ट स्लाइड में देखेंगे. Then stereoscopy, viewing overlapping photos in 3D using stereoscope to perceive depth. So दो इमेज में जो ओवरलैपिंग एरिया है उसको आइडेंटिफाई करके उसको कैलकुलेट करना है, जो फॉर द 3D इमेज creation, that is called stereoscope. So what is the relief displacement? Relief displacement is the concept in aerial photography and photogrammetry that refers to the apparent shift in the position of object in an image due to its height. Suppose this is one of the example. Suppose A is there is no height information in the A point. Then L, K, M, these are some heighted area. So the green line which give the distance between A and L is less distance as compared to the A and in the red line. So this shift in distance of one object due to the height information, this is called the relief displacement. So एक ही ऑब्जेक्ट का बेस एंड टॉप का जो डिफरेंस आता है उसकी वजह से जो हाइट इंफॉर्मेशन डिफरेंट आता है, दैट इज कॉल्ड रिलीफ डिस्प्लेसमेंट. So relief means generally the elevation. So due to the elevation, there is a displacement that is called relief displacement. सेम चीज यहाँ पे भी है. V is the top elevation and U is the base elevation. Then we just seen from the sensor. Then there is a shift in distance from U to V, likewise T to S. So this displacement is called the relief displacement. If the height of the object is more, then the relief displacement is also more. If the height of the object is very less, then the relief displacement is very less. So this is one of the formula for the relief displacement. D is equal to RS by capital H. D is signifies the relief displacement and r is the radial distance from the photo, h is the flying height, and small h is the height of the object. This is one of the formula. So how to calculate the relief displacement? So based on the height of the object and the radial distance of the photo and flying height, we can calculate the relief displacement. This is of this is of the detail of the relief displacement calculation. Then photogrammetry. So generally, photogrammetry is the measure elevation information or getting any information based on the measurement. So there are plane table photogrammetry, earlier it is used, then analog photogrammetry, then analytical photogrammetry, then digital photogrammetry. Nowadays we are using the digital photogrammetry. Then there are two type of aerial photography. One is vertical photograph and one is oblique photograph. So जब satellite image और any aerial photograph में vertically देखते हैं there is no shift in the elevation. तब जब 90 डिग्री एंगल से हम एक कैप्चर करते हैं जो सेंसर से डाटा, देन दैट इज कॉल्ड वर्टिकल फोटोग्राफी. देयर इज नो टिल्ट और देयर इज नो एलिवेटेड, देयर इज नो एंगल ऑफ एलिवेशंस और एनी different angle. That's why it is vertical. So camera axis is perpendicular to the ground, so directly perpendicular to the ground, and ideal for maps and precise measurement. So in the vertical photograph, the measurement is very accurate. So it is also called as the ortho photographs, and oblique photograph also there in the aerial photograph. Like camera axis is at an angle for the ground, and different angles are there. Low oblique photograph, then high oblique photograph, mid oblique. So based on the objective, the angle is from low to high uh, for different aerial photograph. So basically, vertical photograph, which is perpendicular to the ground, and one is oblique photograph, which is some angle to the ground. So these are the difference in the vertical and oblique photograph. These are the example. This is the vertical photograph. Optical axis is 90 degree to the surface of Earth. Then it is a oblique photograph. So the sensor to this Earth surface is some angle is created. This is the high oblique photograph. So these are the some pictures of some vertical photograph. The A photograph is the vertical photograph. Then low oblique photograph, B, picture B. Then C, there is a horizontal, totally horizontal photograph. So likewise, when we taking photograph from different camera or mobile, like this photograph also like this. Then this is the focal length of the lens. Then scale factor is equal to focal length by flying height. So most of time, this some of the problems are asked what is the scale by giving the focal length and flying at altitude. These are given. Then we can calculate the scale. Then the applications. So nowadays, a lot of applications are there by solving and mapping, urban planning, agriculture, environmental monitoring, disaster management, and construction and infrastructure. So aerial photograph are some costly photographs because it is captured by the some aircraft. and it has a huge demand as it is a high resolution satellite, high resolution as compared to the other satellite images. Then we have some basic idea after this. Suppose we have to work with some satellite image, and all the satellite image have the different bands. So different color have the different bands. जैसे कि ब्लू ग्रीन रेड इंफ्रारेड ये सब कलर का डिफरेंट डिफरेंट बैंड होता है और वो जो बैंड का मीन्स दैट्स इलेक्ट्रोमैग्नेटिक रेडिएशंस द वेव फॉर्म and has the frequency and wavelength. Each band, each color band have different wavelength, and it is increasing based on their color. So from blue, green, red, infrared, microwave, the wavelength gradually increases and the frequency gradually decreases. If the wavelength increases, the frequency decreases. So wavelength is inversely proportional to frequency. This is one of the graph, the visible rays, visible color, and different features like water bodies and vegetation soil shows the different characteristics uh, with in different bands. So in the blue color, the characteristics and the graph is different, and for near infrared, there is a high reflectance for vegetations, and for water bodies, there is a high absorption category is seen because infrared absorbs more for the water bodies and reflects more for the green vegetations. That's why we use most of the time infrared band for the forest mapping or mangrove area calculations or water bodies analysis. So look, just see, this is the green, red. These are the bands. There is no differentiations of water bodies, but in the last image, this is the infrared band. So all individual bands are in black and white color. So this last infrared band, it shows the clearly visible the water bodies in the black color because of the absorption categories. So it absorbs more in the water bodies and reflects more in the other features. That's why other features are looking like the bright color, and the water body is black color. So during that boundary demarcation within the water bodies and land part, we use largely the infrared bands. So likewise, different bandwidth wavelengths are there. There is a band one is 0.45 to 0.52 micrometer. So all these bandwidth are in micrometer. So what is the use of blue band in remote sensing? So remote sensing generally in the soil, vegetations, mapping forest types, radiation in this wavelength can penetrate water and are thus used to measure the water depth. So this band has some characteristics that it can penetrate through water. So in the satellite image, we also know the water depth using this blue band and map coastal water areas and detect soil lines. So soil line also analyze in this band. Then green band, so its wavelength is 0.5 to 6 micrometer. It is higher than the blue band. The bands correspond to the green region, which is strongly reflected by vegetation and used to identify plant types and river vegetations. So it is strongly reflected by the vegetations in the green band. Then red band 0.6 through to 0.69. This band can measure photosynthesis activity in plant and discriminate between the different plant species. And it is also used for the soil boundary and geological boundary delineations. But most importantly, that is the band for or near infrared bands 0.76 to 0.90. This band is useful for measuring the vegetation biomass for different mangrove forest or any other forest. So NDVI calculations, normal differential vegetation index calculation, we use the infrared band. It is used for crop identification also. So crop planes are reflect large as it is a vegetation, and land water discriminations also. This is one of the example. You can discriminate land water. Then mid infrared also sensitive to the water and soil mixture. These are very near bands bandwidth are there. Then the thermal infrared, so 10.4 to 12.5 micrometer. It's a larger wavelength as compared to all these. So this band can measure the relative heat or temperature of the objects and can access the stress caused due to the heat. So it can measure the heat information in this bandwidth, in this wavelength. So this is that's why it is called the thermal infrared. And for heat wave and urban heat mapping, I use the thermal infrared. Different Landsat data also there for thermal mapping. Then mid infrared, it is band is useful for discriminating the mineral and rock. So mostly use the multispectral images in remote sensing. After that, we use the thermal remote sensing. So which are the some of the characteristics of multispectral sensor and thermal sensors are we have to discuss now. Then first, the multispectral means more than one spectral bands. So blue, green, red, infrared. These are the four bands need for maximum work. That's why it is called the multispectral. Means multi wavelength images. Blue band, that is one spectral, green, that is one, red, that is one, then infrared band satellite image, that is the one band. So we just join all this band, then create a image which is called as multispectral image. So typically it has 3 to 10 bands. So minimum 3 bands required, or more than 5, 6, 7 bands can be possible. Then thermal band, it detects emitted infrared radiation from objects. So what is emitted infrared radiations and what is reflected radiations? We will discuss later during the thermal remote sensing topic. So these techniques help analyze the vegetation, water, soil, urban areas. So nowadays thermal remote sensing largely applicable to different different zones and different applications. So there is a huge demand in the thermal remote sensing as compared to the multispectral also. So each band captured a portion of the electromagnetic spectrum. So all these are based on the electromagnetic spectrum. Some from blue to radio wave, blue wave to radio wave. That is visible means blue, green, red, near infrared, short wave infrared. So popular satellites which are used these bands are Landsat, Sentinel-2, IRS, Indian Remote Sensing Satellite. It is called as IRS. Then MODIS data. Typical bands use blue, green, red, and infrared. So these are already discussed. Now we've seen that previously yesterday there is a false color image I have seen. I have shown some of the pictures. So these are the bands. So single band, that is blue, green, red. So we just merge it, then create the true color satellite image. So green is looking like the green, white patch is looking like white. So as the ground what is the real uh, pictures, what is the actual pictures of the earth surface. Then satellite image also looks like this, but in the false color satellite image, you just change the green channel to blue, red channel, red band, changes our band to blue, then near infrared to red. Then after merging this, the infrared false color composite. This is the false color satellite image. So in this false color, generally green vegetations are look like red, so that it is easily demarcated, easily identified. That's why we create most of the time the false color composite. So list 3 image, list 4 satellite image of Indian satellite image are all the false color satellite image. So we use this list 3, list 4 image for the forest analysis or agriculture analysis. So this is the false color satellite image, and this is the true color satellite image. So these are the mostly used satellite image. Then different scanners are there. So satellite, when passes through a surface of Earth, then it scan in different way. So suppose it scan in left right direction, then forwarding like this. This is called push broom scanner. And when the scan is like this along the track, then this is called whisk broom scan. So this type of push scanning is there. Then there is the, I just show the increasing energy in the left directions. When the wave, there is electromagnetic wave, there is the wavelength increasing gradually from gamma ray. There is a high frequency and low wavelength. Then X-ray, uh, then wavelength increases to ultraviolet. Then wavelength increases, then to visible range. It increases, and from infrared, it is increases from 1 micrometer to 100 micrometer, the infrared range. Then a radio wave is a larger wavelength, that is 10 to the power 8 micrometer, from 10 to the power 4 micrometer to 10 to the power 8 micrometer. I think it is more than 1000 meter. One wavelength is more than 1000 meter. In the same time, in the blue, green, red, it is zero point 0.5 to zero point 0.6 micrometer. So very large difference between the radio wave and visible rays. So that's why this radio wave penetrates through cloud. So as the wavelength is increases, that have the capacity to penetrating through the cloud or other um, bodies. But when the wavelength is decreases, then they have low penetrating power. So for this all-weather satellite, we use the radio wave and microwave data, which has high wavelength as compared to my infrared and visible rays. So these are the satellite image look likes. So this is the visible range satellite image. Then this is the near infrared. Then there is the short infrared, and this is the thermal infrared. So thermal infrared image is like this. So different image in different bands look like different image. So we have to identify first of all which type of bands are there. So which bands is useful for different applications based on the wavelength, based on the bands we use the different applications. So, so some basics idea we have to know. So, of in the different bands, what is the characteristic of different bands? After that, we will use efficiently. So, in this upper area, there is a thermal infrared range. So it is very much important. So most of the time they ask what is the bandwidth of the thermal infrared. So it is from 0.75 to 1000 micrometer. So it is the range of, sorry, this is the 0.75 to 15 micrometer. This is the range of the thermal infrared. Then applications of multispectral sensing. So different land use classifications and different index are also calculated using different bands like NDVI, SAVI, soil adjusted vegetation index, then EVI, environmental vegetation enhanced vegetation index, that is EVI, our NDVI, that is normal differential vegetation index. So basically, how these index are used. So generally, they are using the bands by mathematical calculation, and they give the one result for different purpose. Suppose for NDVI, there is the method is called near infrared band minus red infrared band divided by near infrared band plus red infrared band. This is the formula. We just uh, minus this near to red of this data of the satellite image, then divide it by near infrared to red. Then there is a value it arises from -1 to 1. So if the vegetation is evergreen or high healthy vegetation, then its value is nearer to 1 or 0.9 or 0.8. But if the vegetation is unhealthy or it is not good enough, then its value is less, like 0.5, 0.4 in this region. For this healthy vegetations estimations, NDVI calculations are there. Then EVI also one of the example. Then SEVI, soil adjusted vegetation index for soil mapping, and so used for the general vegetation and soil characteristics estimations. So these are some of the example. Then multispectral generally used for land use land cover classification. So what is where the river polygons are there, what is the forest area, then settlement, then agricultural land, then all the water bodies and other pond and dams and scrublands and plantation areas. So all these pictures are interpreted with the help of satellite image, multispectral satellite image. Then we can create the land use land cover classification in different scale. So for most of the time, multispectral sensing are used for land use land cover classification. Then agriculture monitoring, crop stress, yield estimation. Then water body detection, turbidity, chlorophyll, soil and mineral mapping, disaster management, flood mapping, and forest fire detection. So these are the example of the multispectral sensor. So this is the NDVI of one of the example. So most of the time, when there is a tree of healthy and there is the tree of unhealthy, so we compare this. So how our bands, different bands react to this. So most of the visible bands and red bands that absorbs in the healthy vegetations, and the near infrared most of the time 50% is reflected, but in the unhealthy the reflection is 40%. So by this estimation we can know uh, the health, which is healthy vegetation and which is unhealthy. So likewise this is the comparison. Then what is the value for NDVI? Suppose this is a stressed dead plant, then their NDVI value is -1 to 0. So this is the range of dead plant or any object. And suppose such one unhealthy vegetation is there, then its value is 0 to 0.33. Then moderate healthy vegetations, which is not as compared to the very healthy vegetation, then its value will be 0.3 to 0.6. Then very healthy vegetation like mangrove plant or evergreen plant, its value will be 0.6 to 0.6 to 1. So we'll see in the practical section, so how to know the healthy and all healthy vegetation with the help of different indexes. So this is one of the estimation of vegetation differences in different years. So in 1991, of a particular area, there is a urban area, and nearer to this urban area, there is a forest area. So this is the situations in 1991. Then after the vegetation degradations and the growth of the population and growth of the settlement, then the settlement area is these areas, then the vegetation area is decreases gradually. Then this is this in 2018. So very less vegetation area is there. This is the situation. So based on the NDVI, we can calculate the vegetation index, forest cover, and some greenery areas. Now, after the multispectral sensor, we go to the thermal remote sensing. The thermal means it is related to the heat and temperature. So in the temperature, how this temperature is recorded in the remote sensing technology, this is the thermal remote sensing principle. So it measures the emitted radiation in the thermal infrared region, typically 8 to 14 micrometer. This is the picture. Suppose this EMR source is there, some electromagnetic radiation from the sun absorbed in the atmosphere, some are scattered in different direction, and some are transmitted, and some are scattered in the cloud region. Some of the uh, EMR are absorbed by the satellite sensor, and some of the emission, that is the earth emits some heat after incident of the EMR. So this heat emission is recorded by the sensor, then create a satellite image, then it give the information of total area, which is the different temperature pattern and is a temperature of a different value. So based on the emission information, if the emission is very high, then the satellite receive all these high emission areas and give the information that this area is a high temperature area. So each area is distributed with the different temperature, and we can create this temperature information with the showing it is a output for different purpose. So detect surface temperature, not reflectance. It is not a reflectance, it is a emission. So reflectance is different thing. So it is a reflection. So the emission, there is a reflection, but emission is different. It is the emission from the Earth's surface. And Stephen Boltzmann law, emission increases with temperature. So this is the law. Based on this law, these are used. Then emissivity is the efficiency with which a surface emits thermal radiations. So surface, which is the more thermal radiation capacity, then it is the more emissivity capacity of this Earth's surface. Then which type of sensors are there? Generally, थर्मल रिमोट सेंसिंग के लिए सब सैटेलाइट इमेज अवेलेबल नहीं है. Some sensors are there, that is Landsat TR, thermal infrared sense satellite, that is TIR, then Astor data, Modis data, VIIRS data. These are available with the help of different bands are there. What is the application of this thermal remote sensing? So generally, thermal remote sensing have a lot of applications like urban heat island mapping. So which urban area has highest uh, temperature in different area of different season, we can monitor and calculate. Then forest fire monitoring. For forest fire monitoring, we can use the thermal sensor. Then volcanic activity detection, and then thermal pollution detection in water bodies, soil moisture estimations, nighttime temperature mapping. All these activities are monitored with the thermal sensor. And military surveillance, energy audit, health of infrastructure. These are also associated applications are there. So generally, this is the image of thermal sensor between the 8 to 14 micrometer. So these are the income sort of radiations from the different features, and it is recorded. So this is the image of same area of different sensor. So left side is the thermal infrared image, and right side is the visible true color satellite image of same area. So in this, we get the temperature information from low, that is uh, given in the blue color, and high in the red color. So it shows the temperature of 14 degrees Celsius to 37 degrees Celsius. So based on the available data at that time, and it is the true color satellite image, that is the urban area. Then it is a river, the blue color river. Then the green patches are some agricultural land which is currently cultivated, and some forest areas are there, and some fallow lands are there. So this is the situation of this land. So generally, temperature is very low in the water bodies areas. So the low temperature shows in the blue color. That's why the blue color, which is in the river area, it shows the low temperature, and the dry land areas and settlement areas, it shows the high temperature. So generally, temperature increases in the settlement area, concrete areas, and dry soil areas, and low temperature is there in the moist soil and some wetlands. So this is the situations of this is the image look like in the thermal infrared band. Then some difference is there. So in multispectral we use the reflected sunlight, and in thermal it is emitted from Earth. Then spectral region is visible, near infrared and short wave infrared or multispectral. But in thermal sensor, only thermal infrared, that is 8 to 14 micrometer is used. So just remember this word, the thermal infrared range is 8 to 14 micrometer. 1 micrometer is 10 to power 8 meter, 10 to power 6 meter. 10 to power minus 6 is 1 micrometer. Then application is LULC, land use land cover, agriculture, water bodies, and thermal is heat mapping, fire, pollution. Temporal use is mostly day. मल्टीस्पेक्ट्रल जनरली हम दिन में यूज करते हैं, क्योंकि नाइट टाइम देयर इज नो use of this. But thermal can be used day and night. This is the difference. And spatial resolution usually higher. In multispectral, there is a higher resolution. In thermal, it is a low resolution, means pixel value differ in multispectral and thermal. This is one of the characteristics of different gases in the atmosphere. So in the different wavelength, different gases behave in a different way. So some gas molecules are absorbed more in the different wavelengths, and for carbon dioxide it is absorbing from 8 to 14 micrometer, and this is the situation. So this is called the atmospheric windows. So some spectral bands, some constituents, and some of the gas absorb more and some emit more. So based on the wavelength, it is the characteristic of the different gases and molecules. Then hyperspectral satellite image. So hyperspectral means larger spectral images. So now our time we just use multispectral means 10 to 12 sensor. जनरली मल्टीस्पेक्ट्रल में 10 to 12 सेंसर यूज करते हैं या मैक्सिमम 20 सेंसर्स बट इन हाइपरस्पेक्ट्रल सैटेलाइट इमेज more than 200 or more than 3 more 100 more than 100 spectral bands are used. This is the different, that's why it is called hyperspectral image. So it means it has the more spectral bands. So why these are more spectral bands? Because we have to, because each in the each wavelength band some features behave like a different way. So to calculate the different behavior of the different materials and different rock type, we use the bandwidth of narrow bandwidth of each band to capture all these informations and reflect in the image. So more than 200 बैंड्स मीन्स क्या है कि सपोज ब्लू बैंड्स है, ब्लू का एक ही बैंड है मल्टीस्पेक्ट्रल में, अगर इसको हाइपर स्पेक्ट्रल में कन्वर्ट करना है तो एक ही ब्लू का 40 से 50 बैंड्स यूज होता है. हाउ 40 to 50 बैंड? सपोज 0.4 to 0.5 micrometer is wavelength of one band of blue band, and within this very narrow wavelength bands are created, then some spectral bands are created. So this is the technique for creation of the hyperspectral remote sensing data. So it is the 100 narrow and continuous spectral bands, also known as image spectroscopy. What is the use? Then identify and distinguish materials based on their spectral signature. So it gives a spectral signature. So there is no other satellite image giving the spectral signature. So it gives the different spectral signature for different rock or different material or different minerals. Based on this, we just understand that this is the uh, iron area or this is the aluminum mining areas. So key difference is the multispectral sensor capture few broad bands, but hyperspectral sensor capture many narrow bands, typically 100 to 400 band. So this is the example of hyperspectral image, and this is the one band, 1, 2, 3 band. So now we can अभी इसमें this left side image is the hyperspectral image. So based on the different narrow bands, we just calculate the different minerals are present. So in this legend, we just calculate there's a keonite and calcite, sericite, diopside, chloride, jarosites, and iron carbonate. So the yellow is the iron carbonate, and cyan color is the calcite, and green color is the chloride. So these are the features. So right side, this creates the graph. This is the unique graph. So for the cull side, always these graphs will be like this. So if we click on the calcite polygon, it gives the graphs in the software. So this is the graph of the calcite. So it is stored in the spectral library, then calculate with the original library and correlate with this satellite image. Then we just identified and confirm so it is calcite or iron carbonate. So likewise for keonite and hematite, all these different graphs are there. So based on these graphs, we can estimate that it is different mineral. So previously we so that only we can identify the features based on the color and association, shape, shadow of the satellite image. But in the hyperspectral image, we cannot identify the features with the help of the color, but we can identify these features with the help of their graph. So it shows some graphs. So if the equal graphs are there, then we can calculate this, then we can estimate and we can estimate the area of the different minerals. So in the lower image, like the true color image, there's the river and some of the vegetations areas. But in the river, inside the river, only one white color image is there. It is a sand area. But in the hyperspectral image, it calculates the different chemical factors and different minerals present in the sand. So it looks like the different colors in the sand area. So it has a high detection value, high detection capacity between each different chemical composition. So it generally detect the chemical composition of the material in the surface of Earth based on their narrow bands. So generally, where blue-green bands are in micrometer, but in the hyperspectral, these are in the nanometer. That means in multispectral, it is 10 to the power minus 6 meter, but in the hyperspectral, it is 10 to the power minus 10 to the power minus 9 meter. So this is the multispectral image and this is the hyperspectral image. So this is the graph of multispectral. This is the graph of hyperspectral. So more bands are there within these bands so that we can calculate the different materials and mineral content of this surface and created this is all these boundaries. So a lot of applications are there in the hyperspectral is very costly satellite image and not available to uh, all areas. Then this is application is mineral mapping. So mostly this is used for mineral mapping and rock type, agriculture also sometimes crop stress detection, soil property analysis, forestry, tree species classification. So different trees have different color and different pattern. So this pattern are detected by this hyperspectral images with very accurately. Then environmental monitoring is there, water quality and pollution detection, military surveillance also use, coastal and ocean studies also use this by the presence of the algae, seagrass, coral reefs. So coral reefs, seagrass and algae are differently identified and differentiated based on their narrow bands and graphs. Then one of the current high resolution hyperspectral image is average hyperspectral data, that is airborne visible and infrared image spectrometer. Uh, this is the airborne image. It is not a satellite image. So that's why its resolution is very high. So, and its spectral range is 400 to 2500 nanometers, and number of bands present is 224 bands. 224 स्पेक्ट्रल बैंड्स आते हैं, बट जनरली हम जो बैंड यूज करते हैं उसमें 3 से 4 बैंड्स होते हैं, बट एवरेज डाटा है 224 spectral bands, and spectral resolution is 10 nanometer per bands, and spectral coverage is visible, near infrared and short. So it's generally visible to short wave infrared के लिए है, and spatial resolution is very high as compared to the other. It is 4 to 5 meter, and for average classic it is 18 to 20 meter. SWAT width, it is 11 kilometers, so it is 11 to 11. So previously we saw that it is 180 to 150, but it is very low dimension due to the high resolution data. So some case studies में ये यूज हुआ था. सो फॉर इंडिया ओनली हिमालय का जो ग्लाशियर मैपिंग है उसमें एवरेज डाटा का हाइपोस्पेक्ट्रल डाटा यूज हुआ था. देन कोस्टल वेटलैंड्स एंड मैंग्रोव्स, चिलिका लागून इन ओडिशा and Sundarban mangrove area are mapped with the average hyperspectral data. And some of the global uses are there in the Amazon forest and California methane leak detections. These are the data. Because it's a very costly data, it's not uh, used by globally. So this is one of the map covering the different minerals, showing the different colors. So this is the hematite, then hydroxide, jarosites. All the minerals are accurately identified with the help of this average data. So no other satellite image can detect these minerals as compared to the average hyperspectral data. This is the airborne sensor, which is used by the NASA. It is prepared by the Jet Propulsion Laboratory of the NASA. This is the path where the satellite image created the image, and this is the image of this satellite, and this is the graph which shows the different pattern of the different mineral areas. So today we have completed the multispectral aerial photograph and thermal sensor details along with hyperspectral. So next we will discuss the microwave remote sensing. What is the microwave remote sensing? Then other satellite data are there. So after that we go to the other classes. So today we will conclude this session. I will meet tomorrow. Thank you. And if any doubts, then ask me.
So tomorrow, what time is the class?
Tomorrow, I think not present. So today is 8. No, no. Tomorrow there is no class, I think. Uh, that the 11th August onwards. So tomorrow is Saturday and Sunday is holiday. So next class is 11th August, Monday. Monday too, we will continue the class. Okay.
And sir, the class is from morning till evening,
Morning.
and is the session recorded? Is the session recorded?
I think it is recorded, but it is not recorded by me. So some IGNU staffs are there. So they have some recorded videos are there.
Because we have office until evening, so I think if class goes on entire day, it will be difficult for us to concentrate and attend.
Okay, I will ask them, so they will provide. Uh, otherwise, we'll take a class for a doubt class for 1 day in a holiday,
Okay.
so that it will.
Abhiman,
Okay.
thank you so
Okay.
much.
Thank you.
Thank you, sir. Thank you.